FA19. I'll go and change the notes, but no bother, it'll be correct in the lecture folder and on YouTube. Yeah, absolutely. Yeah, so we'll talk a lot about that today. So that's one of the key things. So we have an exam coming up next week on Monday and Tuesday. All 4 sections will be in person in class. You guys will show up at the normal section that you do, as will people on the recording. And, oops, that reminds me. Do that and do that, and then I can go back to share again here. Sorry. So you can bring, as you will see in the study guide that I will have next lecture, you can bring the study guide itself, and the study guide will include a bunch of information that you will need for the exam. So if there's tables that I know you're going to need, I'll probably put them in the study guide so that the size of the exam is smaller. So there's less paper to have to grade afterwards. And you can put notes on the study guide. I don't care. I don't want it. So you don't turn it in with the test when you're done. You just have it shredded or framed or whatever it is. Make it into a bullseye or whatever it is you want to do with it. That's all fine. You can also bring a blank sheet of paper with notes on both sides. I don't care how it's made. It can be machine printed. It can be micro dots with a giant magnifying glass. But there's a balance. The more you bring with you to read, the less time you have to do the exam. So my experience has been, and what I've heard from students who've done well, is they'll build a study guide, and that fact alone of constructing it commits a lot of things to memory for them. And then they do well, whether they ever look at it again during the exam or not. Well, that makes sense, right? So if you write it all out, then you're going to remember more of it. So that's a week from today. What we'll spend the entire lecture next time doing is going over the exam. So what I will give you is a study guide that's going to have, you need to know how to do memory references like problem 4 on homework 7, or you need to know how to do stack management like problem 6 on homework 3, or whatever they are. I made those up. Neither one of those problems exists, by the way. And I'll lay them out for you. If it's exactly like one that was on the homework, but the constants are changed, I'll just point you to the problem again. If it's something that's changed, like I synthesize a few things together, I'll go into it in a little more detail, but it is 100% coming from homeworks. So we've studied 3 chapters and 2 appendices so far in the book. It depends on how you want to add them up. We really haven't gotten past chapter 2 in our own textbook and in Zybooks, but we did 7 and 8 in Zybooks, which is appendices A and B, and we used pieces of them, right? So appendix A was the one where we saw the table on how to translate function code into which command you're actually running. And it also had some reference sections in there as well. The green sheet is arguably part of appendix A. That's the card that we look at almost every lecture with the instruction formats and the list of all those things. And then appendix B went into digital logic. And we actually used a couple of chapters for math and then logic from the Stallings textbook to help. So those were helpful. But you can, if you can focus on the homeworks, then great. If you're worried about not knowing some of the homework problems because you work with somebody else and you turned it in, but you didn't ever really get it yourself, wait till the study guide comes out and narrow down what you need to work on. If it's not on the study guide, it's not on the exam. So even with that, the grades will be from like 30 to 100. And that's normal. So we talked about how we curve early in the semester, and that still holds. So you are going in trying to do the best you can. You do not need to get an A to get an A. Very likely there'll be significant lift just from curving things up. So it's the same. You guys, there's so many of you that the population of you is the same one year to the next. I mean, statistically, you are an individual, but as a group, you guys perform similarly one year to the next. So, and it's the same textbook. The words don't change one semester to the next. The same slides. So what's the only thing that's different? Me. I change the way I teach. I change the content and the degree to which we focus on it, the homework problems. So if there's big variations in grades, that's my fault, not your fault, statistically speaking. So you want to do the best you can individually, but I'm trying to compensate. Same thing with TA grading. If you end up with lower homework scores at the end of the semester, and because your TA graded you more harshly, I lift everyone in that TA group up to the average that the other TAs set the watermark for. So nobody's going to get penalized on that just because you have a really hard TA that likes giving out hard scores. That doesn't mean you shouldn't talk to them and try to plead your case. That'll only help you, but it means you don't have to flip out. And I think generally speaking, it's going to require probably 15 to 20 points of homework score, maybe more than that. I'll have to do, maybe we may be looking at a 30-point semester, but you'd have to have a 30-point difference in homework scores, if that's true, to have a 1-point difference in the class. And we can do the math. There is a little estimator out on the class folder where you can put in the averages you think you're going to get on various things, and it'll show you the grade, the number that you're aimed for. And I can't remember, but I may have put in the lift that we used last semester just to give you an idea of what the curve looked like. I don't remember if I did that or not. I've slept since then. It's just, it's just rough. Okay, so we do have some new material to cover today. First of all, any questions on the last homework? I made a mistake on the very, very last problem. I noticed last night when I was rewriting the results for the TAs. The very last problem, number 5D, I think it was a formula that you're supposed to simplify, and the not bar, the second not bar, did not print on your version. It's in the solutions, and all I do is I remove the answers and publish it as the homework. I write the solution version first. Exactly the same, except it has the yellow parts in it. And so for some reason, I took that off somehow. So that problem is not simplifiable. And so I told the TAs just to give everybody the 5 points for that one. So if you just wrote down the same thing, that's correct. That is the actual answer. It's meant nothing. I was hoping for something a little more. Yeah, it certainly, it was a trick question for me too, right? So it's like trying to mess with my own mind, right? So you'll see all kinds of crazy things. I've given out exams with the answers for one of the problems. I've given out the solution to the exam to a student before, and they come back up, Professor, I think this has the solution. They have to think about it, right? Because if you wait 20 minutes to do it, then you're busted. And you can't finish the exam that way because what you turn in has the solutions printed on it already. So it's like one of these quick dilemmas where you figure out pretty fast, you can look through it, but it's not you're not going to remember anything. And so it's just so tantalizingly close to having it. I felt really bad for them, but I was very happy they were honest about it as well at the same time. So do not be surprised at all if I do something like that. It just happens. And my advice to people when I do that is I would write down that answer. It's probably the right one, I'm guessing, because I think that the professor gave that. I came up with the same answer as I just printed on the exam for you. It could happen. While we're talking about midterms, let's talk a little bit about exams. There's a big date difference between exam dates for some of the sections. There's a week difference between the first group to take the final and the last group to take the final. I do change versions of the exams for each class. So, if you come out of an exam and somebody pumps you for like, what's on the exam? What's on the exam? What you're basically going to tell them is what's on the study guide. There was a question on this, and then he had a question on this, and like, that's what's on the study guide. Yeah, it's exactly what's on the study guide. But everything else about it will be different. The circuits will be different. The constants will be different. The equations will be different. The tables, the truth tables will be different, et cetera. So, if you can get money out of somebody for giving them that info, go for it, but spend it fast because it's worthless to them. You're not going to help them anything. Basically, the message is study what's in the study guide. So with that set apart, I try to at least make it even for people. The way we deal with the extra week to study is I typically take a question off of the first exam. So I'll let you pick one that you don't want to do. Walk through the exam and just mark one off that you don't want. I don't really know that one. I'm going to take that one as a freebie. And then we'll grade the rest of them. We'll do something like that to balance out the fact that that section has a lot less time. The other thing I can do is just curve it differently, curve each class independently. So that, and I'll do whatever I can think of that's absolutely fair for you guys. It doesn't put anybody at a disadvantage for the time that you just happen to be assigned by the registrar for taking the test, right? So I try to give you guys a chance to do stuff. All right, I want to spend some time on a couple of other sections here, starting with how we get numbers to the CPU. And this is really a section about addressing, but it starts off claiming it's a section about constants and the lack of a projector screen. So most of the time we need constants in our programs. They are small. We don't use constants that are a billion, for example, very often. So therefore, the relatively small size that MIPS gives us to pass along a constant is usually big enough. It's 16 bits, and it's in the immediate instruction format. It's that last field in the immediate. And this is not the instruction format. What this is showing us is 32-bit number that we would like to construct. And how would you build a 32-bit number? I mean, you could put it in memory and then load it into a register. Okay, well, how did it get into memory? Well, somebody did a math calculation and put it there. Okay, well, what were the operands that they were doing to get the result? Like, were they multiplying two numbers together? Where did those come from? So you get into this chicken and egg problem of where at some point, someone's got to figure out how to get 32 bits into a register before it's already someplace else to put it in the register. So this is a very popular way to do it. And we use the 16-bit constant in a couple of different commands. And one of the commands we use will take your 16-bit constant and put it into the left half of a register. That's what load unsigned immediate does. You can feed it a 16-bit constant. It will take it, it will shift it left 16 bits and insert zeros in the right half. So if I gave, let's see what this number is. This is 62, 61, 61. The reason I know it's 61, besides it's saying it over here, which I forgot about, is if I added one more one, this would be all ones, wouldn't it? And that would be 63, I know, because if there was a 1 here and zeros, that's 64, power of 2. Subtract 1, you turn the 1 to a 0, and you turn all these to 1, and we're almost there. A little trick, to not have to go 1 plus 4 plus 8 plus 16. Just realize that this would have been 64 here, and for the fact that we didn't have 2, we would have had that. All right, so I wrote an instruction that said load unsigned immediate, put it into S0, and put 61 in. So if I go back to my green card, and let's see if I can find it. Nervous when I don't have something open already for class, because it never really works out. It's usually die flames. Here it is. Okay, I got lucky. So there was my luck. You saw it. That was it. Okay, so load unsigned. In this case, it's load upper immediate, so I don't even have the name right. It says LUI. What it's going to do is take the immediate value and start off with that, and then after that, it's going to insert 16 binary zeros. And that makes a 32-bit number, and it's going to put that in register RT. And it's an I-type instruction. So if I go down to the I-types, there's a place for an RT and an RS. I didn't use RS for this instruction. It just said RT and immediate. So if I look at what the command is going to look like, and I build myself a new layer, and zoom this up a little bit, that's why it got done that way. What you're going to find is in your instruction, you'll have a spot in here for the opcode, and we can go look up what that number is. And then there's a space for RS and a space for RT, and then there's 16 bits for immediate. So you're going to put the 2's complement version of the decimal number 61 in here, which is what we just saw a minute ago. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. think is what it is. I may have one too many ones in there. You'll put that there. This, you'll ignore. It has to be, you know, it absolutely is still going to take up 5 bits of your instruction, but we don't care what it is. And if I go back over to my instruction, I wanted S0. So I come back over to Acrobat and look at S0. That is a 16. So I'm going to put the binary version of decimal number 16 in here. And I'm totally okay if you're given a question like this, if you write the numbers just like this. I don't expect you to convert it to binary. You don't have to. You can write 6110 unless I specifically tell you you need to write it in binary. So if you have a calculator that does binary, the decimal conversion, great. If you don't, they're like, you can find it for $8. But if you're going to be ordering it, you need to do it like today, or you won't have it in time. And then remember to bring it. And then as far as, let me do my little lean dive here. As far as load upper immediate, it very interestingly looks like it's just an F. So that's essentially the number 15 in decimal, but you could also say F in hex if you want. Right, so that's the command. If you give this instruction to MIPS, what it's going to do in register S0 is drop in 61 into here. How are you going to get a value over here? The other thing that this LUI command did was it zeroed this out. So the rest of it is kind of clever. What they basically do is use an OR command, or immediate, and they say, I want you to put into S0, well, it's the place we're working, what's already there, and OR it, as opposed to AND it or NOT it or something else. OR it with the number 2304. And so what's 2304? It's 2048 plus 512, or 256 in this case. I think it is 256. So 2048 plus 256 gives you 2304. That's what this number is in binary. You OR those two things together, and what you're going to get is the two orange parts. So if I gave you a problem, and the problem said, if I have this number, 660,480, how would you get it into register T0? How would you do it? What do we need to do to figure that out? That's the result. That's like the two green parts already put together. So, for example, we don't really know what this number is. It's a big number. I mean, it was already 2,304 without any of these bits set. And in fact, we have a bunch more set over here. So this is like bit 17, 19, and 20, 1, 2, 3. So this is a number in the millions, probably. So if I had the number 640,480, and I needed to get it into register T0 using those same two commands, how would you go about doing it? Anybody got ideas? What's the first thing you might try to figure out? Yeah, so you've got, I would even go a step further. I would do the whole number first and just try to turn this into binary, figure out which parts of it fit on the left 16 bits and which parts are going to fit on the right 16 bits. So if I do 600, what was it here? 660,480, and I'm using the built-in calculator on a Mac. There's a version of it that's programming version, and it will show you the binary down here. All right, so this is bit 0 through 32. This thing will actually go up to 64 bits. And what I can see is there's a couple of ones in the lower 16 bits, but there's also a couple of ones in the upper 16 bits. So that's a huge help. So I'm going to take a copy of this, and I'm going to go over to my drawing board. I'm going to paste it in and zoom it up a little bit, maybe a little more. Right, and so here I have it. So what I need to do is get this number into the lower part, but the first step is I need to get this one into the upper part. So what is this number in binary in that left-hand blue box? 10, not some huge millions, because you stop right here. The question is, what is this number right here? And this number is 1010, which is 8 plus 2, 10. Right? Okay, so I got to move 10 into the left-hand 16 bits of a register. And the command I'm going to use to do that is the same one we just saw in this command here. But instead of making it S0, I'm going to make it T0. And the number I'm going to put in there is 10. And that's going to get 1010 in the left-hand 16 bits. Right? Makes sense? And then to do the right-hand part, well, this part's easy. We'll do a couple of T's again. And now we got to figure out, maybe we're lucky, maybe it's 480, but you got to check, right? So this looks like 2, 4, 8, see the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2 to the 10th, which is 1024. And this one is 2 to the 12th, which is 4096. So that's 51 something 20, 5120. And I think that was the numbers on my calculator when I brought it up a second ago, right? So we can try it. We can either type in 5120 and see if we get this pattern, or the thing I like about this calculator is I can just turn off those other bits. We're left with, ooh, yeah, nice, huh? Yeah, I know. You know, I've had a Mac since 1985, and I discovered this last year. You know, it's probably been there for 20 years, knowing me. Yeah, that's exactly my response. Like, Jesus, you got to be kidding me. All these years, and that's been there. I mean, slow down a little, man. Take a look at the program. It's like, and I'd spent probably $300 on calculators over the year, downloading. I had an HP lookalike for 50 bucks, an app on my phone. So yeah, you know, it's like the day I discovered this drawing tool. That was a lifesaver, and a really good scanner as well. So 5120 is the other one. So how do I get that in there? What's the command going to look like? It's still ORI, but now I know the number I got to put here. So if you run these two commands, what you create is a register whose value is, oops, not the right page, whose value is 660,480. Right? Cool, huh? So anybody ever used those commands before in any of the labs or anything? Right? So it's, you guys have probably learned, I would guess, 25, 30 different commands so far without realizing. We'll see a table soon. Okay, so the next section in this has to do with something called PC relative addressing. And really what this is getting at is different ways of building addresses. And I describe it in the homework, but just to give it to you verbally here as well, there is a register that keeps track of where we are in a program. And it's called the program counter. Makes sense? It's got the variable PC, and we actually have permission to write to that register. It's a system register, and you would think it would be protected by the operating system, but we actually have the ability to cause the number in the program counter to change. But what normally happens with the program counter in all systems basically is something that looks more or less like this. What normally happens is you have a number in the program counter, and let's say it's the number 6. And what it does at the beginning of an instruction cycle is your CPU, the hardware, will pull the number out of here, hand it to RAM, into the instruction part of memory, which is a separate part from all the rest of your data, where we put all the instructions in the bottom part so we know to interpret them as instructions. They just look like 32 ones and zeros. How would we know what they are? So we put them in a set of memory that tells us. It means if they're here, it's got to be an instruction. And we will go pull instruction 6 out. And we will pull it back into a register where it waits to be interpreted. It waits to be decoded, as it's called. While that's happening, the same time this is going on, this guy updates the number to 7. Now it's actually a byte address, but we're going to just count up like it's integers right here. So if this instruction that you get back says, I want you to branch in the code to a different location, here's how that would work. Let's say I have my program here, and I've got 6 lines of code. This line of code here says branch to the label called loop end. And loop end, when I wrote it, was a label for, it just happened to be attached to instruction 6. Now, it probably is going to do something as well, but it's not going to do anything if I don't point the program counter down to line 6. So I'm telling it I want you to skip lines 4 and 5. I don't want you to run those anymore. I want you to go to line 6. So the way the compiler will write this code for you is it will put a number in over here that says add or subtract to the program counter some number that will cause me to jump down to here. And so it'll tell it the number of instructions to move down. So my question is, how many instructions do I need to move down? I'm on line 3. Next, I want to run line 6. Yeah, but the reason I ask you is because it's tricky. What about over here? What's in the program counter by the time I realize this is a branch instruction and I read it and I see what it wants me to do? It's already, well, in this case, a bad example for me writing here, but it's already pointing at the next one. Right? So in this case, it's 4, but yeah, it was at 6 and now it's at 7, but in our case, it was at 3 and now it's at 4. So what's actually in my program counter had been 3. Might as well make this match now instead of making it confusing. And so as soon as, while this is happening, the program counter is also updating. But so by the time this instruction comes back, the PC has long since been at 4. It's a little loop thing. It hands off the thing and updates it. Why wait? Right? So it doesn't wait until somebody comes around. It's just like the ice cream shop. You pull the number out, and it tells you, that's your number, and it may be 5 minutes before somebody else comes in, but the next number is already there waiting for them, right? So it's going to already point at 4. Therefore, I don't need to move down 3. I only need to move down 2, right? So the number that you're going to find in the branch command when you write that instruction, it'll say the opcode for branch, and it'll have RS and RT in here, and in the immediate value, it'll have the 2's complement version of a positive 2. Tell it to jump down 2 more. So the program counter actually doesn't have word numbers. This has byte addresses. So this will be something like, tons and tons of zeros, and it'll never be 3 because 3 is not a multiple of 4 to begin with. So it's always going to point to a multiple of 4. Is a word address, the start of a word. And now you want to move down 2 more. So you're going to have to change this. First thing you're going to have to do is multiply it by 4, turn it into 8, and then you're going to add 8 to the number that's in the program counter. You would have added 12, but it already advanced by 4. So now you only need to add 8 more. Right, let me give you another example. What if loop end was up here instead of down below? What if it's up above? And I'm on line 3 and I want to branch up to line 1. What value should I put in here now? So if I put -2 and I go right up to here, but is -2 going to get me there? Yeah, -2 will get me here because I've already advanced the program counter and now it's pointing at 4 already. So I'm going to have to back up 3 to get there. Correct. And so I get back up to here. And so what you'll find in this case is your instruction will contain a -3 and it will be multiplied by 4. It will turn into a -12. And that's what will be added to the program counter. It will, next time this cycle happens, the CPU couldn't care less what number's in there. It just goes and gets it. Whatever address you put in there, that's what it goes and gets. So if you put a number in there that's outside the instruction range, it will core dump on you. That's a check that it will make. Some systems won't even let you put a bad number in there to begin with. But hackers will try to put a bad number in there and just see what happens. Maybe the system doesn't reboot. Maybe it just dumps you out in root mode, command prompt or something. But you then override it with yet another program counter number that points into your code somewhere in the system. But now your code is running as the administrator, because the administrative code that was running, that was supposed to go and get the instruction, crashed, the procedure crashed, and so nobody took it back out of administrator mode and put it back only in user mode. And so you've got your hands on the system, and you can put an address in the program counter that will branch to your hacking code. And it will now run as administrator. So you can do things like dump everything on the stack and write it to a file for yourself or send it over the internet, or go and grab files off the hard drive. You can do anything you want at that point. So that's an example of a way of writing malicious code. Yeah. There's one set of registers per single core CPU for sure. Every core is running its own batch of code. So they are also going to have their own program counter. And they'll have their own full set of registers as well. T's, S's, V's, A's, all that stuff. And the reason why it doesn't completely make sense is because this is a MIPS architecture, and most of the multi-core work we do is on Intel and ARM, but Intel primarily. So Intel's registers don't quite look the same way as these. They do have different naming conventions for them, and they handle them a little differently. But conceptually, anybody that's going to have to go get an instruction has to have a program counter. They have to have a place to put the instruction. So they're going to be sharing RAM. And so there's got to be some care taken. You can let multiple people read out of RAM, but you can only let one person write at a time to an address. And that gets us into cache coherence. We talked a little bit about it before, but one of the things a system has to do if you have a multi-core system, you have to watch for the addresses going by. So the way that this number in the program counter gets to RAM is it goes over a special set of 32 wires called the address bus, and you can watch what goes on. It's like ducks floating by at the carnival on the little tank. And so you can see the addresses that are going by, and you can keep a list of all the addresses that your cores are using. I saw you go get this, I saw you go get that, so I know those two are in use. If I see somebody write to either of those, I will let you guys know. You can go and get a fresh copy of it, because you should stop running because somebody's changed. You guys are out of sync. You think that value had something, but somebody just changed it. So the other thing you can do to keep that minimized a little bit is to only give one program per core. Your operating system could be written to only let one core deal with Word, and the other core gets Excel, and the other core, and sometimes that makes sense. But for graphics programs, you need all the cores running on your one program. So it's much more difficult to write. So what you look for are blocks of code that we talked about last time, a section of code that has no branches into it nor branches out of it except at the beginning or the end. And you can hand that block with confidence to a core and not worry about it branching to instructions that another core is running. Just make sure each core only gets its own part of the program to run. And that's what we do. That's the way we run that stuff. But that's a whole nother set of classes, but it's very valuable because all of our cloud computing that we do, from Dropbox to web pages to anything else that we're going there, those are all lots and lots of users on one server at a time, all running the same one program. You don't run 500 copies of a web server just because there's 500 users on your site. You run one copy of it, and you keep track of 500 users. And you queue them up to different blocks of your code, and you let one person run through a block of code here, while another person's running through this block, and another one's running through this block, and they do different things and use the queuing problem. Right? It's like signing up for, like when I signed up for high school classes, we had a table for each class and had a box with IBM punch cards for that class. And if you wanted to be in the class, you had to go and get one of those punch cards before they were all gone. You would stand in line in front of your most desired class, and you would get up to the front of the line, you would take the card, and you just ran that block of code, and then you go get in another line, all in the same cafeteria, it's all the same process, but you can be doing that while somebody else is doing this. It's a pretty simple concept conceptually, but it's the only thing that makes this scalable for us. It's called multi-threading, for example, or reentrant code, for example. They have different names for them. But ours is simpler, right? So we have one PC, and all we're really concerned about is when we run into something, this is called PC relative addressing because the number that's in here is up or down from wherever the PC is pointing. We don't need to know what the program counter contents are to run that branch command. All we need to know is how much above or below where we are now do we want to move. We can see that at the time we write the code. So the compiler will write the code and it will go, look, I don't know where this program's eventually going to run in memory, but wherever you end up running, once you get to this command, I want you to subtract 12 from whatever address is in the program counter because that's your next command. So there's a final stage when your program gets loaded where they go and resolve all of these numbers. And they will replace minus 12 with the actual number that needs to be there now that they know exactly where the program is. And the next time you run it, it'll do it again and recalculate it. And the next time you run the program, it will recalculate it and do it again. So that's PC relative addressing, otherwise known as branch addressing. We talked about jump a lot already, so I won't spend much time, but this is one where you can get 26 bits in there, and actually we saw how you can really move 2 to the 28th basically from one end to the other because we don't make you give us the full byte address here. We'll just let you give us the word address, and we'll tack on the extra 2 zeros for you. So if you know that all you're going to do is move around word at a time, you can get more mileage out of these bits. So if I told you had 2 bits, how many bytes can you have in memory? Well, with 2 bits, you could say I can have 4 bytes, 0, 0, 0, 1, 1, 0, 1, 1. If I told you that we're in a 64-bit architecture, so all of our words are 8 bytes each, and these 2 bits tell you which word number we're talking about, not which byte number. And you go, okay, so there's 8 bytes for each of those. Well, then it's 32. 8 times 4 combinations of my 2 bits, 32 bytes. Now I can have a system that's 8 times larger by just changing the way I interpret the address. And that's exactly what happens in these systems as well. So if you have a 32-bit system, you would normally think that the number of bytes that you can address is 2 to the 32, right? Which is basically 4 billion, a little over 4 billion. But what if I told you that the addresses that we use inside the PC here, inside the computer, were word addresses, no exceptions? They sometimes aren't, but let's say we did that. Well, then you would have to tell me how big are your words? Well, in my system, in MIPS, it's 32 bits. So each of these 2 to the 32 combinations actually represents 4 bytes each. So the size of memory that I can install on my computer now is actually 16 gig, not 4 gig. So that's how you get these multipliers, and you can have systems with like tons of gigs of RAM, even though they may not have the bit architecture for it. So the way to do math like this would be to say something like 232 times 2 squared, which is the same thing as 2 to the 32 plus 2. Okay, back over to the homework. Let's catch back up now with some problems on where we are. So with PC relative addressing, here's a code snippet that I give you. I'll put an extra space in here, and I need to align this thing back up a little bit. I hate it when it does this to me. The typewriter mode. So here's my branch command right here. Right, so my branch command is sitting down here. So let me see if I can get to do we have enough information to know what value you will find, bad English, I'll have to just look past that, in the constant field instead of the word done when we actually look at this instruction. It's not going to really have the word done. What's it going to have? It's going to have a number relative to where we are for how many words up or down we need to jump. What's that number going to be? So here are 3. So why 3? The first instruction after branch is this. Second one is add. Third one is jump. Fourth one is done. But it's 4 down, not 3 down. Why did you say 3 and not 4? Yeah, That's already pointing to switch, SW. So 3 is correct. Program counter, by the time I read this command, it's ready to load this one. It's already got the address stored in it for this instruction. If I don't do something to stop it, if I don't override it with another number, this will be the next instruction that gets loaded into my CPU. It's about ready to do it. So since I don't want that to happen, I want to branch down here instead. I have to take into account the fact that the program counter already is pointing to here. So it's already done one of the moves for me. So that shaves off one, but if I were to try to jump back up to like top instead, then it would be a negative number. Right? And it would be here. Now, what I don't like about the way they wrote this particular code is there's no instruction in MIPS for a label. Labels don't exist. The label is for us. The label exists in assembly code. So what the compiler and the linker loader will do is they will actually calculate what the address of this instruction is at the moment it gets loaded in, the whole thing gets loaded into memory and it's ready to run. And they will calculate the address this is and replace this number with whatever this address is plus 3 times 4. It's 3 words down. So there's no need for this label because the word doesn't exist anywhere in my program. So what I would prefer they did is actually put something to do after done, like add, T1, something like that, right? There needs to actually be a line of code. Same thing for top. It's a little more problematic here because do I really want to jump up to this or do I want to jump up to this? Because this is really the next command. So if I give you something like this, I'll give you a command next to the label so there's no confusion about it. But I would have preferred had they done something like this instead. Like that. That would have been a little neater to me. Now there's no confusion. Now if you're at the branch and you want to go back up to top, you got to go back one line of code, so you got to figure out the number to put in there to do that. All right, so that's that one. For jump addressing, we've already looked at jump, but I have a question for you guys. We will see in the slides the way the book describes jump is it lets you jump anywhere within something called a text segment. We haven't heard that before. So what they're basically implying is that you can't jump anywhere you want in RAM. You can only jump to places where the first 4 bits of the address match what the program counter is. We know that because it's going to give us those 4 bits and force us to use those 4 bits from the program counter at the top end as our first 4 bits of the destination address. And we worked through that in the last homework. So my question is, how big is a text segment? Well, it's almost exactly the same question that we had before. The text segment is basically, amazing how much I clutter these little things. We have 2 to 32 bits, but we don't have 4 of those because those 4 are going to be kept. And we've got, basically 1 minus this is the maximum address number. And then because we have to align to words, we actually need to subtract 4 off of that. So it's the same answer you had on the prior homework. Exactly the same answer. But now we know a name for it. It's called a text segment. Right? It's a text segment. So my RAM is actually broken up into these segments. And I'll draw a few of them. And the top 4 bits are 0000, 0001, plus 28 more bits. 28 more bits will point you into this. And let's say this is 1111, 1110, 1101, 1100, 1011. So if you give me 28 bits, it will point to a section in this text segment. It'll point to exactly the same spot in all the text segments. So in order to tell me which one of these you're actually talking about, you have to give me the rest of the bits. You have to give me the last 4 bits. These bits here. I drew only 3 here, so 4 bits. Make sense? So you can move around in memory, but you can't move anywhere you want. You can only move around in a segment. So why is that not a problem? Why is that not an issue? Well, two things. First of all, the homework asks you, if these are the leading 4 bits, how many of these segments are there in memory? I have 4 bits to identify a particular text segment. How many are there? Yeah, 2 to the 4th, 16 of them. So do we really have 16 text segments? No. If you remember the drawings we had for how memory is laid out, the part of memory at the bottom where instructions were stored was called text. That's what they mean by text segment. But it's only the bottom part of memory. It's only the very bottom part. So we actually have one segment of memory. So for all programs, for all time, whether they're branches or jumps or just regular lines of code, all of their addresses will always start with the same 4 bits. No exceptions ever. You can't ever jump outside of where instructions are kept. You can't jump there. There is a different jump command that you can use to do it. That uses a register. But all of your code needs to be down in the instruction area of memory. Okay, so that's the answer to that thing. So what I want to do is show you guys an example and kind of walk you through this a little bit. And I think we've got this already, but just to make sure. So here's a block of code, and they did at least intimate that there is something to do here. It's not just a label. So I'm happier with this block of code. It's a better example because the labels are preceded or are followed by actual instructions. And here's some addresses into memory. And the fact that I see these things going up by 4 tells me that these are which? Word addresses or byte addresses? Well, so if these are word addresses, then this would be 4 more words up. It has to be, right? Because we know this is an instruction and this is a word. And we know this is an instruction and this is a word. It's the very next word. So it would be 1 greater. But I see that this number didn't go up by 1, it went up by 4. So these are actual byte addresses to make sure I'm staying on multiples of 4 and therefore advancing 1 word at a time. So be careful, right? That one's a little tricky. Here is a shift left logical, 2 bits of S3, so it's the same thing as multiplying S3 by 4, storing the result in T1. T1 is register, T1 is register 19. Register 9 is S3. This is the number 4 in here because that's what I really want to multiply it by, I guess. And this is SLL. So I think that that might be right. Let's go look and see if shift left logical. Yeah, shift left logical is really 0 and 0. But what I'm confused by is their choice of the shift amount number being a 4. I think that's not what they wanted. I think this number here should be a 2. They're trying to shift left by 2. So I wonder if the authors caught that. You know, I never really know whether to send the typos in because I'm never really sure if they're really that happy with them or not. Because, you know, really. So the next command is add. Then we have a load word. Here's a branch command. And the branch command, if it's taken, is supposed to jump me down to exit. And exit is 1, 2, 3 lines down. But you notice the number that's in the immediate field is only 2. That's because the program counter is already pointing to this add I by the time I run it. And then down here I have a jump command that jumps to loop. And it puts a number in here that is supposed to be 26 bits long. We're going to tack on a couple of zeros. We're going to grab the first bits from the start of this address, which is going to be zeros as well, because this is not 32, 16. No, this isn't 32 bits really either, I don't think. No, it's not. It would be about at least 1 billion if it was 32 bits in size. But this needs to have like a negative sign in front of it, or, so the number here doesn't exactly make sense to me. I'm not quite sure why they put that value, but you guys know that what you're basically trying to do here is put in some number like that, what you're really trying to put in. So I'd have to read through the text associated with this to see if they have a better explanation for why they made it 2. They may say something like, this is from a 16-bit system example, and when you subtract off the top bits, just by a miracle, it ends up being 20,000, but I don't think so. I think it's just a little typo. So depending on the numbers you've got, you can go up or down. If you need to branch far away, then branch equals will get you close. They can get you within the neighborhood. You're going to add or subtract from the program counter. If you need to just replace a bunch of bits in the program counter, jump will do that. So jump can get you a really, really long way off. And therefore, there's a little bit of a summary here, but I'm going to show you a diagram instead of the Stallings book because I like their picture better. If I can find it, here it is. Okay, so we'll need to go into full screen mode for this. As well. I have bricked the machine. Nope, it's coming back. All right, it's. I think on WebEx they're going to be. Let's do this instead. Let's close this off. And zoom it up this way instead. We'll just have to deal with it this way. That's not so bad. So an immediate instruction is one where you give the value directly in the command. And that's an example of passing a number along to a instruction. And the number that you want to pass along isn't so big that you can't actually include it in the instruction itself. So this would be like a multiplication command or something like that where you want to multiply something together. You can have an address as well. You can pass somebody an address to go look at. And if they go and look in that address, they'll find the number that you're trying to give them. And so that's called direct addressing mode. I won't give you the address, the number itself, but I'll at least give you the address where you can go find it. Go look in this place and you'll find the number that I want you to multiply for this, for this problem, for example. Or you'll find the number of times I want you to run the loop, or whatever the number might be. Indirect is one step removed. Now, the advantage of this one is, as long as where you need to move is nearby, then you can point to another location in memory than the one that you're in that's relatively close to where you are. But you can't point to any place in memory because some of the bits are used up for the opcode, for the instruction. So this would be like a branch command. You could move within reason. You're given 16 bits to do it. What if you need to move further away than that? There are a class of commands where you can pass an address that's relatively nearby, and in that address you will find a full 32-bit address in RAM. And it can be absolutely anywhere in the computer. It can be pointing to the far other end of RAM if you want, because it's full 32 bits. And so I can't tell you where the number is, and I can't even tell you exactly where to go get it, but I can tell you who to go ask. Go ask this person, and they will send you to the right location where it's stored. So this is important where you need the system to go and look in a specific 32-bit address, and you don't have enough room to include it in your instruction. So those are 3 key modes right there. But wait, there's more. Take the class now and receive absolutely free set of Ginsu knives. Okay, so here's register-based addressing. This one uses very, very, very little space in the instruction because we have so few registers. We only need 5 bits to point to a specific one. There's only 32 of them. So 5 bits is enough. And so in this register-based addressing, you can have a set of commands that will look at a register number, and they know that what they're supposed to do with it, because the command that you called, is they're supposed to go and look at it in that register number, and they will find the number that you're trying to get. Well, this is what we've done the entire class. If you want to add T1 to T2 and put the result in T0, then that's exactly what you're doing here. This R stands for T1 in this case. You go and look, and you find that the number was really 8. You wanted to do 8 plus 5 and put the result in T0. So put the 8 in a register, put the 5 in a register, and use register-based addressing like an add command. All your R-type instructions use this mode, and you'll tell them which registers to go find it in. So that one's pretty simple. Then there's register indirect, and there are some commands, and it depends on the command. You can't figure this out. You know, the command dictates which addressing mode accompanies it. So if you need a command sometimes to work like register-based addressing and sometimes to work another, then you have to have 2 completely separate commands with 2 different opcode function pairs. You can't have one change its stripes. It's fixed in, it's a rock. It's fixed into silicon. Right? There's no changing on the fly. So there are a set of commands that when you give it a register, it will go and pull a full 32-bit address out of that register and go and find the operand there. So we're building up an arsenal here of options, of different ways of doing things. And then displacement is one that we've used a lot. This is like go 12 bytes past the beginning of array A, and there you will find a number that I want you to add to my total. Okay, so where is array A? Well, array A has a starting address that I've put in a register. Go look there. There you'll find the starting address for the array. And you said you wanted to go past that, right? Where am I going to find the number of places you want to go past? Well, I passed that to you as an immediate. So it's in the instruction. I gave you both the register number and the value 12 because I want you to go 12 bytes past, you know, this. And so you will take the contents of the register, you will add the offset to it, you'll turn it into, you'll multiply it up by 4, and that will give you an address in memory, a full 32-bit address, and you go look in that address and you find an operand. So this one's really popular in ARM and Intel, and you'll find when you look through some of the commands there are lots of variations on this type. Instructions that as soon as they run, they will automatically add 1 to this constant. They will subtract 1 from this constant. They will shift the constant over. They will add 1 to the PC. They will subtract 1 from the PC. You don't have to write a command to do that. There are versions of commands that will automatically do that, like a counter command. There's a counter instruction in ARM where you pull the result out, like what is my counter? What's the value of I? I'm running a loop, and when I gets to 1,000, I'm supposed to stop. So what's I right now? Well, I is 345. Just the very act of asking what the value of I is, it will give it to you, and then we'll add 1 to I. Just like the program counter does. There are versions of those commands in these other architectures that will do that to help you write code that does things like count your way up through a loop or count backwards from a loop. Things that make it a little easier for the compiler author. And then there's one that's sort of implicit. And there are commands to put things onto the register and take things off of the register. Anybody know what they're called? Has anybody run into those words before? Anybody heard push and pop by any chance? Yeah. So that's what it is. All right, I see a question out on Lab 6. You turn in Lab 6 by taking the quiz. That's what it is. I don't know that there's anything else to turn in, is there? Have you guys looked at it yet? I don't think there is. I don't think so. Yeah, there are. But I think the instructions maybe help you prepare for it, but I need to double check on that. But if there's no place on Blackboard to turn it in, then there's nothing to turn in. I mean, that part's easy, right? If I didn't give you a place to turn it in, then walk, right? So, but if there is a quiz at the end of the instructions, there's a button that says begin, and you can take the quiz there. I think that's all there is on it. No, you can take the quiz now because it's ARM based. It's not at all based on the MIPS architecture. It's sort of like a parallel sort of set of, to give you access, give you instructions on 2 sets of assembly instructions at the same time, in the same class. ARM is far more valuable to you commercially in your career, And MIPS is far more valuable to you as a teaching tool because it's much simpler and very structured and regular. So concepts are easier. Intel, for example, has instructions from 1 byte to 7 bytes long. So when you go to load an instruction, you don't even know how many bytes to pull in. It's a nightmare. It's doable. You can get really, really good at it, but it is a huge learning curve. It also has 900 and some odd instructions in it, and tons more addressing modes, and lots of optional flags at the beginning of instructions. So there's many, many versions of each of those 900 instructions as well. So it's a deeper dive. Don't want to use that for starting off with computer architecture. Oh yeah, absolutely. Yeah, you could take the quiz an endless number of times. It's unlimited. So keep taking until you get it right. Yeah, like I told you guys, you should get 100 on every lab. There's no reason not to get 100 on them, unless you just don't do it, or you don't turn it in, or leave part of it blank, or they can't open your. There's already been a ton of people, they've uploaded it and the TAs can't open it, can't read it. Sometimes it's an esoteric compression algorithm that they're using. You should use zip. Or it's just Blackboard, it just does not play the game very well. Takes the ball and leaves. Yeah. So keep check up on that stuff. So again, addressing modes are there. What the rest of this section goes through for us, if I get back over to our slides, is a very similar diagram, right? But a couple of differences in here. They're actually showing you for MIPS the actual, a little more accurately, the command structure. So the immediate ones, they actually show you proportionally correctly that it's half of a command. If it's register addressing, they show you actually, how one of these 5-bit fields points to a register. If it's base addressing, you take the register plus the address and add them together, and then you get to a location in memory. Now, what the byte, half word, and word is implying is that there are variations of commands that will let you go to a word and grab a particular byte. Sometimes you do need a particular byte out of it, but there's a special command. You still go to the word, and then you kind of step your way through and either get the whole word, the first or second half of the word, or the first or second half of the half word. You can do it. There's commands to do that if you need to manage things at that level. So an example of that would be writing text to memory. Each character of text can be written in a byte. The ASCII character set that we use has all the letters we use in English in America and can be represented in no more than 8 bits with a bunch to spare. So each character, if you're writing text out to memory, you're going to do it byte at a time. So if you need to find out what a character was, you need commands that will go into a word and extract a certain byte out, and it will pull those 8 bits out, and it will drop them into a register for you. It will put them all the way over to the right. You'll either put the first byte in there, or the second byte will end up there. So it's like we looked at with LUI, load upper immediate. It grabs it and then puts it in a certain place. So there's lots of commands to manipulate things like that. And then PC relative addressing, this would be like a branch. This would be like an array. This would be for a branch. And then pseudo direct addressing is like a jump. It takes some bits from this and concatenates some bits from this. There's no adding that's done. It's a concatenation. Grab these, stick these in, stick that on the end, and now you have a new address. So those are the ones for MIPS. We're very close to getting back to where we made it a few weeks ago with taking a look at this table. We've already had the advantage of taking a peek at it, but what I want to basically remind you of is how we decode machine instructions. If you're given a 32-bit number and it's written down as hexadecimal characters, you're going to naturally break them up into 4 bits each, just like we see on this slide. AF8020, 6 hex characters, each one is 4 bits apiece. 6 times 4 is, in this case 24, so I left off the zeros at the beginning. But you'll get to 32 bits with this many characters. These are a cakewalk. The ones I'm going to have to work at a little bit are these. So I know these are going to be zeros over here. A, F's not so bad, 8's not so bad, 2. So I can make my way through it. So what I've done is taken each hex character and turned it into 4 bits. But that is not what I want to do to decode machine instructions. What I have to do to decode machine instructions is to reformat this. So I want to do that for you guys. And I want to do it on a new page. So here I have it. The first thing I'm going to need to do is to copy, and re-segment this. So that part's okay, but then I need, then I need these 2 bits. And only once I have these 2 bits, oops. Oh, I'm on the wrong layer. Copy it here and I'll paste it in. Now I have enough bits to go look at the opcode. Once I know the opcode, I know the instruction format. Once I know which instruction format, because I go and look it up, I look up the opcode, I find it over here. If it's a 0, and all the zeros share the same one, it's an R-type instruction. It says so right here on the same line with 0. You see that? R-type instructions are formatted like this. So there's 6 bits, and then there's 5, 5, 5, 6, 5, 5, 5, 5, 6. Boy, you think I'd have that memorized. So here's my opcode. And I have 5 more. 1, 2, 3, 4, rectangle. 1, 2, 3, 4, 5. That's one register. 1, 2, 3, 4, 5. That's another register. Here's the 3rd register. Here's the shift amount. And here are the 6 bits for the function code. Just remember to divide them up differently than the 4 at a time that the hex characters gave you. We'll look at some more of that next time, but you will have a problem on the exam where I give you machine language or hex, and I ask you to tell me what command it is. I will give you the green sheet in the study guide or on the test, but I'll make it, you won't have to bring that with you. But you do need to bring, I get nervous because a lot of people forget to bring the study guide, so sometimes I'll also like print it on the exam because I'm scared that you won't have it. And I don't want 20 people coming up to like, oh, do you have an extra copy? Like I usually will, but so once you get the study guide, what I would do is print the study guide off, you know, the hour before you come to the exam or the night before or something like that. Because I may make edits to improve things even more, to explain things a little more based on interactions I have with you guys over the weekend, and then have a nice final version of it. I won't add problems. I may take problems off. When I write the exam, I may realize that that's too much. I can't cover all these topics that I gave you in the study guide. And I'm going to throw one of them out. So whatever you do, do not spend all of your time on the hardest problem on the study guide. It may not make it on the exam. I've had people do it. I'm like, oh my God, I studied division the whole time and you marked it off the exam. Rather, I kept it on the exam? No. But I didn't study for any of the others. Well, don't do that. Right? So when I told them, go home and study the rest and come take it in the section in the morning. You knuckleheads, don't do that. So spread your time out judiciously. You don't have to get 100 on the exam to get an A. Okay, do dedicate some time to doing it and compare notes on good study guides. Some people will have nice blocks. Oh, that's a great, can I have that diagram to include on mine? Yeah, you should grab that. Okay. All right, guys, that's all I have for today. A little bit short, few minutes short. Yeah. Yeah, so that's homework 7 that we went over. I'll upload it for you, but that's basically what we went over. I will ask you a couple of little questions about this, but that's basically it. No, it won't be due Sunday because I can't give you the solutions then. I'm going to make it due Thursday night. It should take you 10 minutes to do it. And then I can crank out the solutions so you have them to study over the weekend, right? But I want to give you guys another, I want to get this material in, but I have to make it really easy because we don't really have a weekend to go do it in between. Yes, yeah, I promise. That's the last one. So some semesters I've done less than 7 homeworks for the whole semester. Yeah, but this one's a cakewalk, right? So this one's, yeah, and it's like 4 problems or 3, right? So
Someone got on there saying that.
you guys know what catfishing is? I mean, come on, man.
Well,
What you should tell them back is,
like,
what you should tell them is, no, I talked to the professors. There's 3 more coming this week.
do that. It's very annoying. People do that.
But there are people who believe that stuff, and this is a perfect place in college to like get a thick skin and learn how to tune that garbage out. If you can like take a few body blows, and it doesn't hurt.
Over text, there's no way you can tell they're
Yeah, no, but you gotta. Hey, man, those are good skills to develop to detect that. You get to have a BS detector to make it through a career. That's for sure. You're gonna see it. Bye, guys. Where can we find the guide? I haven't printed it yet. The guide will come out.